And what is it we're doing? Well, if we were doing a two-dimensional particle system, we would still be drawing a quad on the screen. We would still be drawing our star or our rain or our explosion or our smoke puff, whatever bitmap we want to draw. But in this case, in 2 dimensions, we would simply be drawing it flat on the screen. And that's fine. That's all we want. That's what we're looking for. But in 3D, it's a little bit more complicated because we're still drawing a 2-dimensional quad, right? That the quad still always has a front side and a back side and an edge, right? But in 3D, and this is a little bit of a tough, complex concept to get your head around, so bear with me. In 3D, what we want to do is we want to draw that puff of smoke or that piece of fire as though it were a sphere, as though it had depth, as though it had 3 dimensions of size. But we're drawing a quad, which has an edge. Why are we drawing a box of particles? Well, number one, a box doesn't solve our problems because it's going to look a little weird. It might be more logical to draw a particle or a quad this way, intersecting a particle this way, and then also intersecting a particle this way to make a kind of a 3D. But that too is actually going to look a little weirder than you think. And both of these ways actually cost 3 times as much triangles as just a simple quad. The key is that no matter where we are in the world, this 2-dimensional flat quad, we want it to face you. We want it to face the camera. We always want, no matter where the camera is, we always want to face. We don't want a camera placed in such a way that the particles are edge onto the camera, because that doesn't look right. That looks weird and teary and stuff. We want the particle to automatically turn to face the camera no matter where the camera is in the scene. How do we do that? Well, with matrices is the usual answer in 3D, and that's what we're going to do. If we look at this code, we have an inverse projection matrix. That's what we've defined it. And it's very simple. We take the view matrix, which in this project we had already made as a matrix that just shows where the camera is. And we invert it, which is part of the step. The other thing is we're going to rip out the position that's inside the matrix, leaving only the rotational data. And this inverse rotational matrix is what we're going to use to make sure that all the particles always face the camera. We get a copy of the graphics device, and we do these 2 key things. I've just talked about a list of the different things that we can use particles for. Missile trails and smoke and rain and fire and explosion and torches. Most of these things have something in common, and that is that they're hot, they're self-illuminated, they're burning. And there's a way in computer graphics to easily make something look hot and self-illuminated. Normally, when we draw pixels on the screen, we draw in what is normally called replace, where if we have a screen that's full of blue and we're drawing a 2-dimensional 2D texture full of brown, then whenever we're drawing a single pixel, we replace the blue with the brown. And now we've got a brown dot, right? That's called a replace. When we do translucent textures, we still have a replace ability, but we also have the source bitmap having an alpha channel, which we've talked about before. It's the A value, which is the translucency value. If it's full A, then it's fully opaque, and if it's 0A, then it's completely transparent. So that means that full A means the dot is brown. No A means it's transparent, means the dot remains blue, right? Because the background was blue. And if you have 50% translucent, then the dot will wind up being the average, the 50% of brown and 50% of blue, which will look a little bit dark purplish, I think, but But the point is that that's how we blend pixels. In fact, that's called a blend mode. And the blend mode is sometimes called opaque or translucent or sometimes just default, because that's the normal way we draw things on a computer screen. Whether we're doing in 2D or 3D, we're down at the level of drawing individual pixels. And in individual pixels, the normal way we draw them is replace, and sometimes replace translucently. But there's a completely different way to draw, and that's called additive drawing. And additive drawing at the very lowest level is very primitive and very simple. Instead of doing a replace, you do an add. And this add is done on the individual color pixels of the image, which means that the source image and the destination image both have red. Those two get added together. And then the source and the destination have two green values for that pixel. Those get added together. And then the same for blue. So you get these individual red, green, and blue values of the pixel. Source and destination simply get added together. Now, wait, you say, there aren't that many, there isn't that much space in a pixel. You, Tom, said that each pixel, the RGB values, were normally represented on the computer screen with a single byte going from 0 to 255 levels. And that's all you got. Well, you're absolutely right. Absolutely right that if you have a source pixel of white and a destination pixel of white and you sum them together, you're going to go over. If you have 255 white and 255 white in the source and destination, and you add them together, what do you get? 255 and 255, 510, I think. And that's way above the limit of 255. And there are different ways that the computer could theoretically handle this, but graphically speaking, for the additive mode, which is a standard mode for most video card drawing, additive mode, we clamp the value at 255. In other words, if our source color is 100 and our destination color is 200, then we add them together to get 300, but since that's higher than 255, we stop it at 255. We only let it go as bright as 255. We don't wrap it around to 0, we don't clip, we don't do anything else with it funky, we just stop it at bright white. And that's okay, that actually tends to work out just fine for additive drawing. What does this do? This additive drawing has a lot of very interesting aspects to it. One, it tends to make graphics that are very hot and self-illuminated. It's perfect for fire, it's perfect for flame, it's perfect for explosions. You almost always see your fire and your flame and explosions being drawn additively. Here's another aspect of additive drawing. It doesn't use alpha channel because there is no calculation for alpha channel. Since the two values are summed, they're not averaged, and the alpha channel is used in the averaging calculation. So they're not, there's just the source value of red and the destination value of red, the source value of, and the destination value of green, and so on for blue. These are just summed together, and that's it. So if you have a bitmap that you want to draw on the screen, and it's intended to be drawn using the additive drawing process, then you don't care whether that bitmap has an alpha channel. The alpha channel means nothing. It's not used in the actual drawing calculation. And this also means that if you want a bitmap that is drawn additively but is very translucent, very faint, you don't adjust the alpha channel. You simply draw down the brightness of the image because it's about summing. Okay? Now, one other really cool and interesting aspect of additive drawing is that it really is additive, which means that all other things being equal, when you actually get done drawing all these particles, and you're going to draw a lot of particles, and they're going to be fairly in the same place, like coming out of a rocket motor, so they're going to overlap one another. When you're in additive mode, your since don't necessarily really care which one you draw first. And in fact, since we're doing something kind of similar to translucency, we're drawing these particles in a way that should not actually touch the Z buffer. Remember, we had a discussion about the Z buffer. It's a 3D aspect of all of our video cards that allows us to draw and obscure different triangles that we draw based on order of distance from the camera. And this is normally a good thing, but we don't want our particles participating in the Z buffer depth sorting, because number one, all the particles, no matter which way or in which order they get drawn, they still look really good when they're drawn additively. But also because you can generally see through particles, especially additively drawn particles. And because of that, we don't necessarily want them drawing and adjusting the Z buffer. So I just got through saying that we're using additive mode, which is a special mode you can use in 2D or 3D to make your graphics very hot and very self-illuminated, very bright. We always generally want to use additive mode when you're doing fire effects or flame effects or sometimes even smoke effects. But we also got through saying that in this 3D world we're making, we're going to make each individual particle always face the camera, not edge onto the camera. And we're going to make these particles not actually affect the Z buffer, which means that if my head is a 3D mesh, which is drawn normally, not additively, and then I put a bunch of particles in front of me, I would hope that I draw the particles last, because otherwise they'll appear behind my head, even though my head is theoretically further away from the camera than the particles. So generally by rule, we exempt particles from writing to the Z buffer, but not exempt them from reading from the Z buffer. And we always try to draw the particles last. With those two rules, we can usually keep it straight so that the particles exist in the 3D world and are drawn in ways that look like they have form and location. So as you can see again, this is why we draw additive, setting the device, and depth read. In other words, not depth right. Alright, and then we set the texture of the effect, and then we loop through all the particles drawing them. So what are we doing when we loop through all the particles? Of course we don't want to draw anything that doesn't have a life left. Here's where we actually calculate the color of the particle. We're taking the original color of the particle and we're multiplying each of its 3 colors by life left. In this case, life left divided by 100. And then we set a couple of matrices for the effect. And in this world matrix, we create translation position and then say world matrix times inverse projection, which as you recall is the inverse of the camera matrix that we borrowed so that we could get this situation of all the particles always facing the camera. And then this is a for each pass in the particles that calls a function called device user indexed primitives. So we're doing basically what the function says. We're going to draw some primitives, in this case triangles. It's an indexed primitive, which we'll get into later in a little more detail, but means that we have some vertexes and we have some references to those vertexes that individually make up the triangles. And of course user means we made this set of triangles in our code. And that's true, we are going to draw that way, and we're going to draw with these arguments using the point list and the triangle array list indices, and the way we're going to draw is called triangle strip. So in 3D it's worth going over that a little bit, because in the very primitive level of drawing triangles onto the screen, we actually have a set of choices. And you can go look this up in EXNA or 3D instructional text you might find. There's maybe half a dozen different ways in which we can take our vertexes and stick them on the screen. And we have to, when we draw them on the screen, we have to tell the video card which method of drawing we want. Obviously, one of the simplest is to take 3 vertexes and draw a triangle, right? Single triangle, 3 vertexes. And we could actually draw 6 triangles using, we could draw 2 triangles using 6 vertexes, or 3 triangles using 9 vertexes. You know, 1 triangle after another, you know, 3 at a time, basically. That's called a triangle list, and that is one mode for drawing with your video card. A triangle strip is where you go alternate. You define your first triangle as 3 vertexes. And then if you want to draw one more triangle, you add one more vertex, and the previous 2 vertexes are added to that last vertex to make a new triangle. And then, boop, here's another triangle made of one more vertex, and so on. So you get this strip or belt-like pattern of triangles, and beyond your first triangle, which took 3 vertexes, now each new triangle only costs you 1 vertex. As you can see, this is why video cards came up with these interesting ways of drawing triangles, because you're talking about throughput efficiency, especially when you're talking about triangle fans and triangle strips. You're talking about much more efficient ways of getting a long series of triangles off to the video card to be drawn quickly. Okay? But there's a few other things. For instance, you can draw actual points. In many video cards, you can draw little pixel dots just by giving individual vertexes to the video card. And you can draw lines. You can draw 3-dimensional lines through 3-dimensional space by giving it sets of 2. And you can have a line list and also a line, a line list and also a line strip, if you know, the similar way you have a triangle strip. So there's these different ways of pushing triangles to the video card, pushing vertexes to the video card so that it interprets those vertexes into the triangles or lines or maybe even points you want. And normally, things are just drawn with triangle list or sometimes triangle strip if the data is right. We're using a triangle strip because that allows us to make a quad with exactly 4 points sent to the video card. So, we have drawn, and this is it. This is the whole thing, which basically shows that for all of our 1,000 particles, if the particle is alive, we draw 2 triangles and a bitmap onto the screen. And again, we draw that quad, those 2 triangles, in such a way that it's always pointed at the camera. So now this is great, and this is happy, and there's nothing wrong with this, except that setting up all this stuff and doing the matrix and calling for each pass apply and draw index primitives, we're doing this for potentially 1,000 particles, and that's actually a lot of work. If we were doing it smart, we would make a giant triangle list of 2,000 triangles and draw all 2,000 at once, just in one draw. We would call user draw user index primitives once for all 1,000 particles. That's a different way of doing things. It's not a bad way of doing things. It has its own headaches, like what do you do with all the particles you allocated that you didn't actually put into the data. But ultimately, what this shows is that this is not the be-all end-all of the particle system. This thing that I wrote, 3dparticlesystem.cs, is not the best particle system. It's a good particle system. It's a very useful and general purpose particle system. But when you get down to it, different particles used in different games require different ways of thinking and have different priorities. So you're not going to have one particle system piece of code that works for all particles for all games. But this one works for what it is for now. And there's one more function, which is a very important function, both conceptually and functionally. and it's called emit. So if you ever actually read up on particles across the web, you will come across this concept called the emitter. And the emitter is actually very important. The class or object in the game that generates new particles. Now, when I say generates new particles, and graphically, we're thinking about sticking an emitter on the back of every missile, and on the back of every spaceship, and in the center of every fire, and in the center of every explosion, and right on the top of a torch hanging off a wall. This is where particle emitters should be placed. And in a very object-oriented world, that's exactly how you would think. You would create a particle emitter, which would exist only to generate particles, because that's what an emitter does. Now, in the code that I've written here, and in the code that I write in general, I actually prefer a simple emit function, so that any object in the game that happens to want to have flame coming out the back, or an explosion or whatever, the object itself can call the emit function and thus be an emitter. So you won't find an emitter class in the 3D particle system.cs object that I've written here. But many other particle systems you will, and that's okay. Just keep in mind that an emitter's job is to emit. The idea of an emitter is to generate particles, generally speaking, over time. I mean, not necessarily in the case of an explosion, where lots of particles are generated that fly off in all directions individually at once, and then boom, the explosion's over, right? But in things like smoke and fire and flame and rain, particles are continually being emitted over time. Every single frame you emit a few particles. And this is what this function allows you to do. If you want a flame coming out of the back of your rocket, then every frame your rocket calls emit. And it's very simple. It says start point, that's where the new particle should start. And velocity, that's the direction and speed the new particle should fly off at. And the color of the new particle. So this code is pretty simple. All it does is it actually goes through and tries to find the next dead particle in the array of 1000. Because once we find it, then we're done, and we can resurrect this particle as our new particle with a new life, a new position, new velocity, and new color, all sent to us by the arguments of the function. And I use next particle as a cool way to try to predict what the next dead particle will be, which works pretty well. That's all it is. An emit function just makes one particle, which means if you want to make an explosion using this particular piece of code, you would probably wrap your emit function in a loop of, say, 100 or 200 or 300, not 2000, because we know that this particular particle system is set for 1000 particles. So wouldn't it be dumb to try to make more than 1000 particles at a time? The system can't handle it. So that's it. That is the code for the 3D particle system that I added to the previous FPS Boxy project. And remember that the way that the particle is going to look on your screen is controlled entirely by you. First off, in the setup function, there you go, texture name. You've got a texture that's going to be drawn additively on every quad particle. And so that texture should usually be something like this, which happens to be flare1.png. So let's look at flare1.png. I can zoom in here. So this texture is really cool in some significant ways. First off, it's the size of it is a power of 2, 64 by 64 pixels. So it'll fit well in the video card and not have any problems. Number 2, notice it is white where you want it to be bright and black where you don't want it to be bright. So remember, I was just saying that in additive drawing, your alpha channel doesn't mean anything and is not useful. All we're doing is taking the red, green, and blue colors and summing them with the background red, green, and blue colors. So this is what this particle takes advantage of. The area around it, the box, is all black so that our particles don't look boxy. And the particle itself is whitest and therefore going to be hottest in the center. So it's going to look very natural. It's going to be looking like a flaming ember or flaming particle, just like we want it to be. So when you make your own particles, the bitmap that you base them on, of course, is going to define a great deal of how they look. But not all they look, because you're also going to emit particles over time. And this emitter takes 3 arguments: where the particle starts, which direction and speed the particle goes in, and what color the particle is. In other words, if I wanted to make a red flame, then my color should be red. And if I wanted to make a blue flame, my color should be blue, and so on. If I wanted to make a particle that comes out the end of a rocket, then every time I should call emit, the start point should be wherever the end of the rocket is, right? In 3-dimensional space. And if I wanted to make an explosion, I would call emit a whole bunch of times, maybe 100 times, just, for instance. But the start point should all be the same, right? The center of the explosion. However, if I'm making an explosion, I don't want all my particles to not only start in the same location, but go in the same direction. In fact, I want them to go in wildly different directions. So I would randomize the velocity. I would actually use a random number generator and fill in the blank with random x, y, and z velocities for where the particle is going to go. That would actually allow the particles to fly off in all different directions and make a really nice spherical explosion, right? On the other hand, if I were making rocket exhaust, we wouldn't want to do that, would we? Because the rocket doesn't necessarily always shoot off in all different directions. In fact, we usually make a trail of fire, don't we? And since we assume that the rocket is going to go in a direction and move it, rockets are usually, they're usually on the move. They're seldom stuck in one place. What we can do with a rocket exhaust is generate particles that don't move very much, but we keep generating over time. So the rocket moves, and as it does, it lays down a trail of individual particles that don't move very much, but fade off and die. And in this way, the rocket exhaust does look like it's actually flaming in a direction, which is to say, away from the rocket, when in fact it isn't. It's just the rocket moving along. So you get that even with just the bitmap, the color, the starting position, and the speed and direction of the particle, you can actually get a lot of cool and interesting different effects out of particle systems. And that's, again, the reason I love particles so much, is because a basic piece of code that quickly and easily does its job and can be quickly and easily inserted into the update and draw functions of your larger existing program can be used in so many different ways to draw so many different cool, usually hot, special effects. So, and that's why I love it. That's why I've always enjoyed building and using particle systems in my video games. So hopefully I've given you an understanding of what particles are and showed you one implementation of particle in code, and given you the understanding of the basic principles of how particle systems work and how particle systems are supposed to be designed so they can be efficient and easy and fun to use. So thank you for watching, and keep watching my videos. Bye-bye.